Okay, so over this lecture and probably the next one, we will see the promised linear lower bound for the randomized complexity of disjointness. Okay, so we have seen the square root and lower bound by Babai, Frankel, and Simon, and today we will see the linear lower bound. So we have seen this the randomized lower complexity of disjointness is at least square rooted. And for this, we actually relied on distributional complexity, right? We showed one distribution such that uh, any distribution, any protocol that makes an error for some constant error has to use at least square root and complexity, asymptotically square root and many bits. And if you remember in one of the live classes, in the classroom lectures, we had shown a protocol where Alice and Bob rely on shared randomness and they together determine the disjointness, the function disjointness using so disjointness restricted to k-sized sets. So Alice has a k-sized set, Bob has a k-sized set, and they can exchange order k many bits and infer whether the sets are disjoint or not. So this was by Vigderson, I think, and okay, I forget, but it is. I think it was by Nissan and Vigderson. I think I'll correct it later. So the point that I want to make is that the the lower bound used the uniform distribution over sets of square root n, and we have a protocol that uses k bits, order k bits, to determine disjointness when the input is restricted to sets of size k. So which means for this hard distribution over here, square root n sized sets, we could use this protocol to get a order square root n protocol, right? So which means that there is an order square root n protocol for this distribution for which Babai, Frankel, Simon you proved the lower bound. So this means that for this set, you cannot do any better in terms of achieving a better lower bound. So getting a better lower bound using distributional complexity will require you to have rely on some other distribution. Okay, and further, it is also shown that I think Babai, Frankel, Simon in the same paper, I think they showed that if you take any product distribution, so even this is a product distribution where each of Alice and Bob took a set of size square root n uniformly at random. So for any product distribution, it was shown that there is a protocol of complexity square root and log n, right? So this means that if you need a linear lower bound, you have to rely on not just any distribution, but you have to rely on a distribution that is not a product distribution, because we have a square root and lower bound, and for any product distribution, we have a square root and log n protocol. So to get so for any product distribution, you cannot get a lower bound better than square root and log n. So to go to a linear lower bound, we need to go to a non-product distribution, right? So today we will see the linear lower bound, and this was first proved by Kalyanasundaram and Schnitger, and soon a simplified proof was presented by Razborov, both in 1992. And what we will see here is Razborov's proof. Okay. So we'll run distributional complexity, and we'll show a distribution which requires you to exchange linear many bits. So what is the distribution? So let n be equal to 4l minus 1 for some integer l. Okay. So the distribution is simply this. So before you read what I've written here, the distribution is that either Alice and Bob have two inputs that are disjoint, or they have two inputs that intersect in exactly one element. So the distribution is uniform distribution over all disjoint inputs and over all the inputs that Alice and Bob have that intersect in exactly one element. So either they don't intersect or they intersect in just one element, not more. Okay, so now you see why it is not a product distribution. If you had a product distribution, then you cannot get such a distribution, right? So this is the distribution, but the same distribution we presented in a bit different way, but it's exactly what I said. So instead of picking a random distribution in random pair of disjoint sets or random pair of sets that intersect in exactly one element, we'll do it a bit differently, but it is exactly the same distribution. There is, even though the presentation is different, it is the same, right? So you partition this n into three sets, T1 and T2 of size 2L minus 1, and the third set is a singleton set containing an element I, right? So, and this partition is chosen randomly. So you can think of any way to do this, just that T1 and T2 must be of size 2L minus 1 and third set should be a singleton set. And now once you made the random partition, Alice's input X is a subset of T1 union I and Bob's input Y is a subset of T2 union I. So notice that T1, T2 it's a partition. So T1 and T2 are disjoint sets of size 2L minus 1 and the left out element is, so 2L minus 1 plus 2L minus 1 is 4L minus 2 and the left out element of N is I. So X and Y are such that X and Y are both subsets of this, and notice that T1 is 2L minus 1 size, so together this is size of size 2L and this is also of size 2L, and you want to pick a L-sized set X from this and an L-sized set from this. So there is a small correction in what I said earlier. X and Y are either disjoint sets or they intersect in one element, but they are always restricted to those sets which are of size L. Okay. So X and Y, so it's what I said plus with the condition that X and Y are of size L. Okay. So now that distribution and this distribution are equivalent because essentially you could so notice that now when you pick X and Y, either they don't intersect or if they intersect, they intersect in exactly just the element I, right? Once the partition is fixed. But then they could intersect in any element according to the random, because I could be any element which is chosen uniformly at random. So yeah, so effectively what this distribution turns out to be is X and Y are of both of size L. Either they don't intersect or they intersect in exactly one element. Okay, so now if you recall in the Bebel-Frankel-Simon theorem, we had shown that the distribution of zero inputs and one inputs were both a constant fraction, and that's the same case here. Let A be the one inputs set of one inputs with non-zero measure, and B be the set of zero inputs. And we'll soon see that both of them have constant probability of occurring. So as I said before, if X and Y are in B, which means it's a zero input, which means they are not disjoint, it means that X intersection Y intersect, which means that they must intersect at I, right? Because that's the only way they can intersect. So mu is the distribution, okay, this I already have said, such that A is a set of all disjoint pairs with both X and Y of size L, and B is a set of all pairs with X and Y of size L, such that they intersect in exactly one element. Okay. Now we will prove the main lemma, which will help us prove the theorem. So this lemma is actually kind of similar to the corruption bound. And this lemma and the proof of the theorem is what we will see first, the statement of the lemma and proof of the theorem. And you'll see that the arguments that we use are very, very similar to the corruption bound argument that we saw earlier. But nevertheless, I'll go through it. It is just the same kind of arguments but rearranged in a different manner. But anyway, we'll go through it. So the lemma is this: let R be any rectangle. Okay, and so B is the set of zero inputs, right? That those that intersect. A is the set of one inputs, those that are disjoint. Then the measure of B intersection R, right? So a rectangle in the matrix. The measure of B intersection R is at least a constant times measure of A intersection R minus 2 power minus delta n for some constant alpha and some constant delta, both non-negative, both positive. So what we are saying is that consider R be any rectangle in the set of inputs that Alice and Bob can receive. Now look at the intersection of this rectangle with the set of zero inputs and the set of one input. So any rectangle, you look at how many of what is the contribution of zero inputs to that rectangle and what is the contribution of one inputs to that rectangle. And what we are saying is the contribution of zero inputs is at least alpha times the contribution of one inputs minus something. So what does it mean? It means that if the measure of the rectangle, the total measure of the rectangle is greater than this, then measure of A intersection R, this cannot be small, this also has to be, okay, measure of A intersection R the maximum this can be is this. Sorry. Okay, so the point is this. If the measure of the rectangle is this, can this be an all ones rectangle? The answer is no, because if this is an all ones rectangle, then that means all the inputs are members of A, right? A is that of all ones inputs. So in which case, the entire measure of the all ones inputs, A intersection R, is actually equal to the measure of R. In which case, this is 2 power minus delta n divided by alpha. In which case, this is at least 2 power minus delta n, and this entire thing is strictly greater than 0. Which means, assuming we started with the assumption that it's an all ones rectangle, and then we are getting the conclusion that the zero inputs in that rectangle has some strictly positive measure, which is contradictory. So that means that any rectangle of measure bigger than this, right, that is not too small, has some zero inputs, right? So if the rectangle is slightly bigger than slightly big, then it has zero inputs. That's the inference. Now using that, we'll show the theorem. So why does it follow? Because we have a distribution. Every rectangle that is not too small, that is not too small, has some zero inputs. So now we cannot get two. Now there is a fraction of one inputs in the rectangle, right? In the entire the total, there is a total fraction of one inputs, and we said that it is a constant. And in fact, we'll see that the constant is equal to 3/4. So now this, you cannot have two big one rectangles, because if there are two big one rectangles, then this is a problem. Too many zero inputs creep in, and that leads to error. So we have to have small one rectangles, and that contributes to the complexity of the protocol. Okay, so first we will prove the theorem using this lemma, and the rest of the lecture is going to be the proof of this lemma. Okay, so first we are going to prove the theorem, that is that the disjointness requires randomized complexity of disjointness at least linear. Okay, so suppose, in fact, we are going to argue on the distributional complexity. So suppose, so for this distribution, let's assume that there is a deterministic protocol which has a low error. So for that deterministic protocol, let R1, R2, etc., RT be the rectangles for which the protocol announces 1 as the answer. Right? These are the rectangles for which the protocol announces 1 as the answer. Okay. So now, okay. So T is a partition. Okay, T is the partition, that is T1, T2, I. So once we fix a partition T, so first let us try to understand the composition of the 0 inputs and the 1 inputs. Once we fix a partition T, what is the probability that X and Y are intersecting, and what is the probability that X and Y are disjoint? Okay, so what is the probability that X and Y are intersecting? The probability that X and Y are intersecting is for both X and Y, I is a member of X and I is a member of Y. So what is the probability that I is a member of X? So notice that I is a member of X means, so what is the total number of choices for X? So X could be an element set from this T1 union I, which is a 12 element set. So total, there are 12 choose L possibilities for X. So that is there in the denominator. And how many of them contain I? So let's say we fix I as one of the members of X. Then we have to pick L minus 1 elements from the remaining 2L minus 1 elements in T1. So the number of X that contains I is 2L minus 1 choose L minus 1. So what is the fraction of the elements that contain I? Once we fix T, it is 2L minus 1 choose L minus 1 divided by 2L choose L. If you just write out the binomial coefficients, you see that it is half. So probability, and the probability that I is in Y is the same. Exactly same calculation, that's also half. So the probability that X and Y intersect is the probability that I is in X and I is in Y, which is half times half, which is 1/4. So that is the measure of the 0 input. Measure of B is 1/4. So everything else is a 1 input. So measure of A is 3/4. Clear this calculation? Now, again, now what we are going to see now is exactly like what we saw in the corruption bound argument. Now, recall R1, R2, RT are the rectangles for which the protocol announces 1 as the answer. So how much of the 0 inputs can creep into those, into the R1, R2, etc., RT, into the RIs? Well, if the total error parameter of the distributional complexity protocol is epsilon, the measure of zeros inside the RIs should not be more than epsilon. So that's what I've written here. Epsilon should be greater than, or the measure of zeros in the RI, that is B is a set of 0 inputs, union this or intersection the RIs, it should be at most epsilon. Okay, now let us understand the right hand side. What is this? This is just the summation. RIs are it's protocol partitions, right? So RIs is a partition, so you can just add up B intersection R1, B intersection R2 and so on. So you get this because it's a disjoint union. Okay, and then now we have the condition that of the lemma, right? We are using, recall we are using the lemma to prove the theorem. So we have the assumption that for any R, any rectangle, we have measure of 0 inputs is at least measure of alpha times the measure of 1 inputs minus this, right? And certainly the rectangles, the 1 rectangles of the protocol have to abide by this. This is true for any rectangle. So we can write it as alpha times the measure of A intersection Ri minus this. And the second term here is not dependent on I, so we can just write T times that. And alpha could be taken out of the first term, so you just have the summation. Now let us try to understand what is this. What is the measure of 1 inputs in all the RIs? So recall, these are the entire set of rectangles which are announced as 1 rectangles in the protocol. And we know that the total measure of one inputs is 3/4. Right? Mu of A we saw here is 3/4. And the total error allowed is epsilon, at most epsilon. So you cannot be too far away from 3/4. In fact, this has to be at least 3/4 minus epsilon for the protocol to be a valid protocol with error parameter epsilon. So this should be at least 3/4 minus epsilon. So you may recall that this is exactly the same kind of argument that we did for the corruption bound. So you get this, and now just rearranging the terms, we get that. So now this epsilon is greater than or equal to this. So if you just take t to the other side, epsilon minus epsilon here, you get that, and you multiply both sides by 2 power delta n. So here now it's the minus is gone, 2 power delta n times 3/4 alpha minus epsilon times 1 plus alpha. This is just basic algebra, is what you get. And we can choose epsilon adequately small and take log base 2 to get that. Log t is at least delta n plus this. So why are we choosing epsilon small? We are choosing epsilon small so that this quantity is a positive quantity, right? Because here we have alpha times 3/4. We choose epsilon to be significantly small, something like, let's say you choose it as 0.01. Then this quantity is very small. Right? Alpha is also going to be something very small. So this thing will be very close to 1. So you get that this is a positive quantity. So log of that positive quantity is also a positive quantity. So this is at least, or log of that positive quantity is well defined. Right? That's so maybe this is a negative quantity, but that's okay. It's a constant. So you have delta n plus a constant. So that is log t, and t is the number of rectangles used. So the height of the tree is at least log t. So which means, and this is a general tree. We are not using any. We took an arbitrary tree that satisfies this error parameter epsilon. So that means for any tree that satisfies this error parameter, this has to be true, and hence the distribution complexity is at least this. So this is how we show that the distribution complexity is at least linear. Okay, so I hope this is clear. So one of the key, I'll just again recap. The partition, once you fix a partition of 4l minus 1, t1 has 2l minus 1, t2 has 2l minus 1, and I has one element I. And x is a random uniformly chosen L element set, and y is also a uniformly chosen L element set of this. So now if they intersect, that means they intersect at I. What is the probability that they intersect? If for a fixed value t, it is 1/4. So this is true for any fixed value t. So now you can so this must be true overall also, because you can think of the protocol as first choosing a t and then doing this, but then whatever be the first t, the next part is 1/4. So whichever way you choose t, the next part is going to be 1/4. So the measure of the 0 inputs is going to be 1/4, and measure of 1 inputs is 3/4. Right? So this is the probability that I is chosen next, and which is half, and the probability that I is chosen y, that's also half. And then the probability of the 0 inputs in the one rectangles cannot be more than, the measure of 0 inputs in one rectangle cannot be more than epsilon. And then you rewrite this, and this comes from the lemma, this part. Mu of b intersection ri is at least mu of alpha times mu of a intersection ri minus 2 power minus delta n. And rearranging terms, we get this. And since the measure of one inputs is at least is 3/4, this cannot be smaller than 3/4 minus epsilon. Otherwise, the protocol will have made an error of more than epsilon. And hence you get this, which can be rearranged to delta n plus constant by choosing epsilon adequately small. And that's how you get the linear lower bound for disjointness. Okay, so now what remains is the proof of the lemma. So I first prepared the notes, and then I saw that the proof of the lemma is kind of long. So yeah, so I prepared. Then I inserted a page 3.5, which illustrates the roadmap of the proof of the lemma. Okay, before I get into the proof, let me just say that um, I am kind of faithfully following what is there in the book. Okay, the book has a very good representation of this in section 4.6. Section 4.6 of the book is exactly this proof, but section 4.6 of the book is just going to prove this lemma, and uh, and if you look at exercise 3.22, where it's a worked out exercise, they have proved the rest of the arguments, which is what we have kind of said, but kind of uh, more crisply than what I have said, not in so much detail. So so most of what I'm saying is already there in the book. It's just the writing, whatever I've written is kind of, you can see that it's exactly kind of like what is there in the book. There are some few places where I've written a bit more, but it's more or less faithful to what is there in the book. Okay, so now this is something that is not there in the book. There is a roadmap of the proof of lemma 1. Because proof of lemma 1 is kind of long, so I thought having such a roadmap will help us will help us understand it better. So this is what we want to show. For any rectangle, the measure of 0 inputs has to be at least some constant times the measure of 1 inputs, right? Using this distribution. So first we define something called row T and column T. So what does that mean? So that means, see, you have a rectangle and that lemma has to hold for any rectangle. So now, given an arbitrary rectangle, row T and column T measure how much does each partition, right? So the rectangle is fixed. Now there could be several partitions, right? Because the distribution is that you first fix a random partition and then you pick an x and pick y. So how much does a random partition contribute to R? Right? So now suppose R has a mixture of inputs, and the partition T is chosen in such a way that most of the inputs in R have half the elements in T1 and half the elements in T2. Then these don't contribute anything, because the contributing elements in R to the measure mu are only those for which the rows come from T1 union I, right? So so again, we'll see all of this in more detail. So row T indicates how much does each partition contribute to R, each partition T contribute to R, and column T indicates the same. And then we'll see that row T is half of row 0 T and row 1 of T, where row 0 of T is the contribution from disjoint inputs, and row 1 of T is a contribution from intersecting inputs. So here is something that could be a bit confusing to all. Uh, why? Because disjoint inputs, the function, if if the inputs are disjoint, the function evaluates to 1, and the inputs are intersecting, the function evaluates to 0. But then row 0T and row 1T are defined opposite. However, most of my notes were already prepared, and plus the notation in the book is also like this. So let us just live with this inconsistency. Row 0T corresponds to those to 1 inputs which are disjoint, and row 1T corresponds to 0 inputs which are intersecting. So we'll just live with this. So row T and column T indicates how much does each partition contribute to R. Okay. Step 2, we will define something called bad partitions that don't behave well. So the good partitions behave well. So bad partitions are kind of hard to deal with. So we'll define some partitions which are bad. So then we prove claim 1, which says essentially that most partitions are good. Okay. So claim 1 will say that most partitions are good, and claim 2 will say that so it is not enough that most partitions are good. The contributions from the good partitions are significant. So claim 2 will show that the contributions from the good partitions are significant. And all of this will be in terms of row 0 and row 1 and column 0 and column 1 and these kind of parameters. But lemma 1 is actually in terms of the measure mu B intersection R, A intersection R. So claim 3 will relate the measure A intersection R in terms of row 0 T and column 0 T, and B intersection terms R in terms of row 1 T and column 1 T. So and now this will translate the definition of, so we have already seen that most partitions are good, and we have already defined bad partitions, and this this relation that is provided by claim 3 will translate the fact that most partitions are good into the statement of lemma 1, which will say that the collective measure of across all partitions mu A intersection R, or sorry, mu B intersection R is at least alpha times mu A intersection R minus something. So this is the roadmap. First we define this row column, which are how much does each partition contribute to R. Then we'll define bad partitions, and then we'll see that most partitions are good and that the contributions from good partitions are significant. And then we'll see this relation, and then we'll put it all together. So what seems like a good plan is to defer the proof of claim 1, which is the out of all this a bit more involved, and we'll prove claim 2, claim 3 and the final statement. Claim 1 will be proved in the lecture 33. Okay, so now we will work towards the proof of the lemma. Okay, so let's say that we are given a partition T and rectangle C cross D. So R is equal to C cross D. So now we define row T to be the probability that X is in C given T, given that we are in the partition T. Row 0 of T is a probability that X is in C. X is a member of C, given that the partition is T and that I is not an X. So row 0 means I is not an X, and row 1 means I is an X. So again, as I said before, C is fixed, the rectangle is fixed, so R is fixed, C and D are fixed. Now what is the measure that this rectangle, this partition or a particular X that is there in this rectangle contributes to the measure mu? So to understand that, we'll take an arbitrary partition T and see if what is the probability that X is in C. So notice that, let's say X has half elements in T1 and half elements in T2, then it will not contribute anything. It will contribute something only when X's entire set of X is contained in T1 union I, right? And here it will contribute something if it is in T1, and it will contribute something if it is in T1 union I, but necessarily contains I, right? So that is the definition of row T, row 0, 1 T, and row 0 T and row 1 T. And similarly, we have column T, column 0 T, and column 1 T. Instead of X, we have Y, and instead of C, we have D. Everything else is same. Okay, so now let us make some observations. What is row T? Row T is the probability that this. Now we can further condition it on I being in X and I not being in X. So X is in C given T and I being in X, and multiply with the probability that I is in X, plus probability that X is in C, T, I is not in X, and multiply with the probability that I is not in X. So we have already seen that if you pick a random set X, right? We have already seen it here. If you pick a random set X, the probability that I is in X is half. So this is half. And this is also half because the probability that I is in X is half. So the complement event also has half probability. Which means, and this is row 0t and this is row 1t. So it is just nothing but half times row 0t plus half times row 1t. And similarly, column t is equal to half of column 0t plus half of column 1t. That is observation 1. Observation 2 is that suppose there are two partitions T1, T2i and T dash, T prime is T1 prime, T2 prime and I prime such that T2 and T2 prime are the same. Okay, T2 and T2 prime are the same. The first claim is that column 0 of T is equal to column 0 of T prime. Why is this true? Column 0 of T is when Y is chosen from D. The probability that Y is in D and that I is not in Y. So which means Y is entirely contained in T2. And for both these partitions, T2 is the same. So it doesn't matter how T1 and I are distributed. So this is only dependent on T2. So column 0 of T and column 0 of T prime are the same. Likewise, row of T and row of T prime are the same. Why? Because row of T is the probability that X is in C given T. Now T changes in both places, but X is in C. So what is the probability of choosing X? The probability of choosing X is a random element from T1 union I. But we know that T2 is fixed. T2 is same in both of these, which means T1 union I and T1 prime union I prime are also the same. So T1 and T1 prime may not be the same, but if you together these two are the same as these two together, because T2 is the same. So the rest of the elements have to form T1 union I prime here as well as here. And what is the probability of choosing a random set X from that set? It is the same whether it is here or here, right? So row of T is equal to row of T prime. So notice the difference here, it's column 0 of T, but here it is row of T without a subscript. Similarly, the same argument in a symmetric manner gives us that if T1 and T1 prime are the same, then you get row 0 of T equal to row 0 of T prime and column of T equal to column of T prime. Okay. The third observation, okay, is that for all T2, okay, let's say we fix a T2, then the row 0 of T given T2 is equal to the row the expectation of row 0 of T given T2. So what I mean here is expectation over all the row 0 of T such that T2 is fixed. This is equal to the expectation of all the row of T given T2 is fixed, right? So why is this case? So both places I am taking the expectation with a fixed T2. So the reason is that let's say T2 is fixed. In this case, what is the distribution of row 0? What is the distribution here? So this boils down to what is the probability that X is in some C, right? Now X is in C means X has to be in T1. But then T1 is randomly chosen. Another way to think is T2 is fixed. So the choice of T1 is also the choice of I, right? Once I is fixed, everything else is T1. So row 0 of T is you're taking all the possible L element subsets of T1 here. But then T1 itself is randomly chosen. So which means you will see all the L element subsets with equal likelihood. And here we don't have this zero subscript, so which means here here also we will see all the L11 subsets with equal likelihood. So hence the distribution of the x's in here as well as here is the same, because I is anyway not fixed, so we are considering everything. Hence the expectation of this is the same as the expectation of this. So summarize the observations. Rho of t is the probability that x is in t given x is in c given t. So roughly again, consulting our roadmap, rho of t indicates the contribution of a partition t to the measure of R. Rho 0 of t and rho 1 of t put together constitutes rho t. This indicates rho 0 of t indicates the contribution of kind of inputs that are likely to be disjoint, and rho 1 of t indicates the contribution of the inputs that are likely to be intersecting, right? And similarly, column t, column 0 t, and column 1 t. The first thing is that rho t is half of rho 0 t plus half rho 1 t. Second is that once t2 is fixed, column 0 t and column 0 t prime will be the same, regardless of what t and t prime are. And rho t is equal to rho t prime. And similarly, when t1 is fixed, rho 0 t and rho 0 t prime are the same, and column t and column t prime are the same. The last observation is that once t2 is fixed, the expectation taken of rho 0 t over all t2, the same as the expectation of rho t taken over all t2, taken over t2. So this means the expectation is taken over all the partitions t which has a fixed t2. Fine. Now we will define the next step of the roadmap. What is a bad partition? So recall in our lemma, we said that most of the rectangles, if it is not small, contains a significant fraction of zero inputs. And the bad definition is essentially kind of trying to capture that. So recall I said rho 1t is kind of the measure of contribution of the inputs that are likely to intersect. Okay. So and column 1t are the measure of the inputs that are likely to intersect. So we want, ideally as per the lemma, we want the zero inputs, the intersecting inputs to be at least some constant times the disjoint inputs. So those that do not kind of follow that are called bad inputs. So here the intersecting inputs rho 1t is strictly less than rho 0t divided by 3 minus 2 power minus delta n. This is the same delta n that is there in the lemma statement. So we say that a partition t is x bad if rho 1t is less than rho 0t divided by 3 minus 2 power minus delta n, and y bad if the column 1t is less than column 0t divided by 3 minus 2 power minus delta n. And we say that t is simply bad if it is either x bad or y bad. If it satisfies one of the two conditions, we say it is bad. What I have not written here is that if it is not bad, we say it is good. So if it is good, it will satisfy that rho 1t is greater than or equal to rho 0t, etc., and column 1t is greater than or equal to column 0t, etc., etc. And that is kind of like the statement that we said in lemma here. Rho rho 1t is greater than rho 0t and column 1t is greater than column 0t. What this lemma statement is saying is that the contribution of zero inputs is greater than or equal to contribution of intersecting inputs times a constant. Fine. For the good inputs. Okay. So and then we define indicator random variables, bad subscript xt, bad subscript yt, and bad t, that indicate whether these are random variables that indicate whether t is x bad, y bad, or bad. Fine. So t is x bad if this is satisfied, y bad if this is satisfied, bad if either it's x bad or y bad. And these are random variables, which means if t is x bad, this will be 1. If t is not x bad, this will be 0. Y bad, this will be 1. If it is not y bad, this will be 0. If it is bad, this will be 1. If it is not bad, this will be 0. So claim 1 is that once t2 is fixed, the probability of bad x being equal to 1 is at most 1 by 5. Or in other words, for a fixed t2, the probability that t is x bad is at most 1 by 5. And this is symmetrically we can say this. For a fixed t1, the probability that t is y bad is at most 1/5. Okay. So this is the claim, that is step 3 in our roadmap, that says that most partitions are good, because there may be 1/5 partitions that are x bad, 1/5 that are y bad. So at most 2/5 that can be bad. So 3/5 are going to be good. So we will this takes up a big chunk of the space. So we'll prove this claim at the very end. So first we will prove claim 2. We'll state and prove claim 2, claim 3, and then the lemma. And the proof of claim 1 will be in the next lecture. Okay. So the next claims are not that difficult, or not that difficult to see at least. It is just basic algebra and some probability ideas, along with all the observations that we have made. This says that the contributions from the good partitions are significant. Okay. Claim 2 says the contributions from the good partitions are significant. So what is row 0t, column 0t? The expectation is taken here over all the partitions t. Row 0t times column 0t is at least 1/5 time row 0t, column 0t. So here there is 1 minus bad t. So this will have a weightage only if the partition is good. If the partition is bad, then bad t will be 1, and this will not contribute to the expectation. So whatever is there in the left hand side here, the contribution occurs when the partition is good. So this is the contribution of row 0t and column 0t when the partition is good. So I could have written it given that the partition is good or something like that, or multiply. So for the good partitions, we see that it is at least 1/5 times the expectation of this. So this is what I mean by significance. So it's a constant fraction. Okay. So we'll show it in a slightly different way. So we'll instead show that. So we can rearrange this and show that the expected value of row 0t, column 0t, bad t is at most 4/5 time expectation of row 0t and column 0t. So then by linearity of expectations, this will follow. Fine. So it's enough to show this. Now, bad t is an indicator random variable that says whether t is bad. T is bad if it is either x bad or y bad. And we have the corresponding indicator random variables bad xt and bad yt. So if this is bad t is 1, if this is 1 or this is 1. So we can write like this. If both of them are 1 also, this is 1. If either one of them is 1, this is also 1. So instead of showing this, we will actually show that expectation of row 0t, column 0t and bad xt is at most 2/5 times expectation of row 0t and column 0t. And because of symmetry, this will also be true for bad y. Bad x replaced with bad y. And adding these two, you get this. So all that we have to show is this statement. Expectation of row 0t, column 0t, bad xt is at most 2/5 times expectation of row 0t and column 0t. So in other words, it's saying that the contribution from the bad x partitions or X bad partitions are no more than 2/5. And similarly for Y bad partitions. And so there are, for the good partitions, at least 1/5. Okay. So what we will do here, is argue conditioned on a fixed T2. Okay. And this will be true for if this is true for a fixed T2, then it is true for overall also, right? So let us take the expectation of this quantity for all the partitions such that T2 is fixed. So this means that expectation of this quantity rho 0t, column 0t, bad xt, given T2 is fixed, meaning the expectation is taken over all the partitions T such that T2 is already decided. As per observation 2, we said that once T2 is fixed, column 0 T is equal to column 0 T prime. So basically once T2 is fixed, the column 0 T value is fixed. So let it be called CT2. And we also saw that the row T value is fixed. Let us call it RT2, because this is fixed once the T2 is fixed. So row T is RT2 and column 0 T is CT2. Okay, so now first we can take out, so this is a constant for all the partitions with T2 fixed, column 0T is a constant. So we take out column 0T as a constant CT2, and then we have this. And now by observation 1 says this, right? Rho T is half of rho 0T plus rho 1T. So now we can easily infer that rho 0T is less than or equal to twice rho T. And that's what we are going to use here. Rho 0T is at less than or equal to twice rho T. This follows, right? Observation 1. So you get this. So the column 0T was taken out as CT2. Rho 0T is here. Rho 0T gets replaced as 2 rho T. And now rho T is also fixed. Rho 0T was not fixed, but rho T is fixed, which is RT2. So we'll take out 2 and RT2. And what we have here is expectation of bad xt given T2. Okay, what is expectation of bad xt? Expectation of bad xt, it's an indicator random variable. It's a 0-1 random variable. So expectation of bad xt given T2 is the same as the probability that bad xt is equal to 1 given T2. So expectation of a quantity of a 0-1 random variable is the probability that it's 0 times the probability that it's 0 plus 1 times the probability that it's 1. So basically it's just the probability that it's 1. So expectation is equal to the probability that this is the case. And we know that this is at most 1/5 by claim 1. So this is at most 1/5. So we get that it's at most 2/5 times CT2 RT2. Now that we have got what we wanted, now let us try to get the right hand side, which was 2/5 times expectation of rho 0T column 0T. We already have the 2/5 here, so this is expectation. I'll take this inside rho T given RT2, and we know that rho T given RT2 by observation 3, rho T given this is rho T given T2. So we know that the observation 3 said that rho T given T2 is equal to rho 0T given T2. So we write that, we substitute this with rho 0T given T2. And now we take in the column CT2, which is column 0T. And we have the right hand side that we wanted. We wanted 2/5 expectation of rho 0T and column 0T. But just that we proved it with for all the partitions with T2 fixed, but that's okay because this holds for all the partitions with T2 fixed, so it holds for all the partitions also. We can take for each T2 this holds, so this holds for all the partitions. Fine. So first step was to observe that rho T and column 0T are fixed. Then we took out CT2, and then we used rho 0T at most 2 rho T. Then we got this 2 times CT2 RT2. Expectation of bad X is nothing but the probability T is x bat, and which was, once T2 was fixed, we know it's at most 1/5 by claim 1. So we get this, and then we take in rho T, which is, the expectation is equal to expectation of rho 0 T given T2 by observation 3, and then we take in CT2 to get this. So we have the left hand side that we wanted, and that completes the proof of claim 2. So this shows that the contribution of the good inputs is significant. Significant meaning it's a constant fraction. So recall, in our roadmap, we have defined rho 0 T, rho 1 T, etc., rho T, column T, all that. And then we define bad partitions, or we define good equivalently, we could say we define good partitions which kind of align with what we want to prove in the lemma. Then we are seeing that we said that the total fraction of bad partitions are small, and then the contributions from good partitions is also a significant fraction. And now we are going to, but then all of our findings are related to this. Now we will translate it to the terms of the lemma, where we had the measure of B intersection R and A intersection R. And this translation is given by claim 3. Okay, claim 3 states that mu of B intersection R is 1/4 expectation of rho 1 T column 1 T and 3/4 expectation of rho 0 T column 0 T. Let's see. First conditional expectations, mu of B intersection R is mu of B given mu of B multiplied by mu of R given B. We know that this term is 1/4. We said that at the beginning. And then let's try to compute this. Measure of R given B. What is this? This means that X. So let's try to understand what is measure. Measure is, there is a rectangle, and what is the problem? So we know that what is the fraction of R inputs that are coming from, or what fraction of 0 inputs are in R, right? So B, if you recall, B is the set of 0 inputs, right? And right, let me just check. This is B set of 0 inputs, yes. And we are, what fraction of the 0 inputs are in R? So in other words, if you pick a randomly chosen xy according to the distribution mu, if we know that xy is in the set B, what is the probability that xy is in R? Okay. So what do I mean by xy is in B? So this means that they both intersect in the element I. So I is not really a very good statement to make, because we don't know what is I. I depends on the partition. But at this point, we have not fixed a partition. So let me fix a partition. So I can write it as summation over all the partitions T, the probability that the partition T was chosen, multiplied by xy is in R, given that the partition is chosen, and given that I is in both x and y. Fine. This is a probability that it's a 0 input. Okay. Now once I fix the partition, and now I am insisting that I is there in both x and y, then the choice of x and y are kind of independent, right? I could pick any x and I could pick any y that is independent, because I've already divided T1 and T2, and I've told that, so it's about picking L-1 elements from the remaining 2L-1 elements for I, and same for y. Sorry, L-1 out of 2L-1 elements for x, and same for y. So the choice of x and y are independent. So I might as well write it. So R is C cross D, recall. So I might as well write that x is in C and y is in D. So I write this as a product. The probability that x was chosen to be in C and y was chosen to be in D. And now, whether I is in y does not really matter for the choice of probability of x. So we can drop this I in y here. And similarly, the fact that I is in x does not matter for the probability of y. So we can drop I is in x here. But now that we have reached here, this is nothing but rho 1 of t and this is nothing but column 1 of T. So just we can recall row 1 of T is probably X is in C given T and I is in X. And same for column 1 of T. And now we are taking expectation over all the T. So this is just, we are summing up over, so it's just expectation of this quantity. So we have proved the first part, which is that mu of R given B is expectation of this, mu of B is 1/4. So the product is mu of B given R, mu of B intersection R is 1/4 times expectation of row 1T and column 1T. So the next part, mu of A intersection R, is very similar. So one thing we can write, mu of A intersection R, it's very similar, but there is a small twist or small step that needs to be understood. So A intersection R, recall, is a set of one inputs or a set of disjoint inputs. Okay. So if we consider the partitions, right, all the partitions, and all the partitions such that, and all the xy such that I is not in X and I is not in Y, we would have considered all the disjoint X and Y uniformly. What I'm saying is, once we are considering all the partitions T1, T2, I. Look at the partitions where I is not in X and I is not in Y. So this will be disjoint, and I claim that this is a uniform distribution over all the disjoint XY of size L. Because if you pick any X and Y, in disjoint X and Y, there will be some, there will be equal number of I for which are avoiding that, and so it's uniformly distributed. For any disjoint X and Y, it is distributed uniformly. So what I'm saying is, for mu of A intersection R, we will likewise compute mu of R given A. So for R given B, we wanted intersecting input. So we had the condition that I is in both X and Y. But here we may think that we want to write the three conditions: I is not in X, I is not in Y, or I is in X but not in Y, I is in Y but not in X, I is in X but not in Y. But the point is that we can restrict ourselves to the partitions ourselves to the cases where I is not in both X and Y, and that still we will be considering all the disjoint X and Y uniformly. So that's the key insight that is needed here. So mu of A intersection R is this, and we have already seen that mu of A is 3/4. So now we need to compute mu of R given A, and by the argument that I just made, mu of R given A is summation over all the partitions T, probability of T given this, and here we don't need to write I not in X, I not in Y, I not in X but I in Y, I in Y, I in X but not in Y. That kind of thing we don't need to write. This is sufficient, right? And likewise that we did here, we can likewise write this. We can again, by the same argument, it is independent, because once we fix T, it is independent X, and so we can split this, and we can drop I not in Y from the condition here and I not in X from the condition here. So what we have left is row 0T and column 0T, which is the expectation of row 0T and column 0T. And together with mu A, we get the required bound that mu of A intersection R is 3/4 time expectation of row 0T and column 0T. So now we have proved this. Mu of B intersection R is 1/4 time this, and mu of A intersection R is 3/4 times expectation of row 0T and column 0T. So now we have reached step 4, which is that, or step 5, which is that how to relate the row T, row 1T, row 0T, column 0T, all that to the measure of B and measure of A. Now what is required is to complete the proof of lemma 1 using claim 1, 2 and 3. In fact, we just using claim 1, 2 and 3. Uh, in fact, claim 1 is not explicitly being used because we use claim 1 in the proof of claim 2. So we'll use this claim 2 and 3. Okay, so we start with measure of B intersection R, which by claim 3 was 1/4 row 1 expectation of row 1t and column 1t. Now I can write this as 1/4 row 1t column 1t times 1 minus bad t. So what I'm really saying is that I am only going to be considering this expectation for the good partitions. For bad partitions, this will for bad partitions t, this term will kill the entire expectation. Okay, entire contribution to that bad partition t. For good partition t, this will sustain. So in another way to see this is that I'm restricting the expectation to, or I'm only considering the contribution from the good partitions t. So when bad t is 1, then this everything gets to 0. But when bad t is 0, this contributes. When bad t is 0, we know that the t is good. And what is the definition of being good? The definition of being good was it is row 1t is greater than or equal to this, and column 1t is greater than or equal to this. So I write that again here. Row 1t is greater than or equal to this, and column 1t is greater than or equal to this. So I can write that now here. Mu B intersection R is at least 1/4 times this times 1 minus bad t. Now using a small bit of algebra, so basically this is row 0 t by 3 times column 0 t by 3 minus 2 power this times column 0 t by 3 minus 2 power this 2 power delta n times this plus something. So let us ignore the plus term because it's a positive quantity. So it's anyway greater than or equal to. So I can ignore the plus term. The minus term is minus 2 power delta n times this and this. So it's an addition. But we know that rho 0 t is a probability and this is also a probability. So two probabilities put together is at most 2, but we have divided by 3, so at most 1. So the entire thing comes out as minus 2 power minus delta n times 2 by 3. But anyway, this is greater than or equal to inequality, so I drop the 2 by 3. So I subtract a bigger quantity. So I get this. And now that I have this, I can take out the 1 by 9 constant term outside here. Okay. Now we have the expectation of row 0 t, column 0 t, 1 minus bad t. And this by claim 2, expectation of row 0 t, column 0 t, 1 minus bad t is 1/5 of expectation row 0 t, column 0 t. So by claim 2, we have this to be at least 1/5 times this. So I write that. And what is the expectation of row 0 t, column 0 t? Again, by claim 3, expectation of row 0 t, column 0 t is equal to, or mu of A intersection R is equal to 3/4 times this. So this is 4/3 times this. So I write it as 4/3 times measure of A intersection R minus 2 power minus delta n. And the 4's cancel and the denominator is multiplied to 135. So alpha is equal to 1 by 135. And recall we had the left hand side was mu of B intersection R. So thus we get the statement of the lemma. Again, so just to revise this, the proof of the lemma. By claim 3, this is B intersection R is 1/4 row 1t, column 1t. I first restrict this expectation to the good partitions t by multiplying by 1 minus bad t. And when the bad t is 0, we can use the conditions that are satisfied for the good partitions, which are this. So I replace row 1t by this and column 1t by this. And now by a bit of algebra, it is easy to see that I can bring out the minus 2 power minus delta n here. There is an additional term that gets cancelled, or that gets ignored, that gets subsumed in this thing. And now I can bring out the 1/9 Rho 0 t column 0 t times 1 minus bad t is at least 1/5 times expectation of rho 0 t column 0 t by claim 2. And this is equal to 4/3 times the measure of A intersection R by claim 3. And this is the constant alpha, which is 1 by 135. And thus we get the statement of lemma 1. So let's just, now that we have seen, let's see the roadmap again, and we'll just see that what we have done. So first we defined rho t, column t, rho 0 t, column 0 t, all that, which are supposed to indicate how much does a partition contribute to R. Okay, and then we define bad partitions that don't really align with the cause of the lemma. Claim 1, most partitions are good. Claim 2, the contributions for the good partitions are significant. Claim 3 relates the measure of A intersection R with this and measure of B intersection R with this, and the last step was put everything together. The first rho t was defined, column t was defined, and then we made this rho 0, column 0, all that, and we made these observations. Rho t is this, which is equal to half of rho 0 t plus rho 1 t. And similarly for column t, and then we made the observation that when T2 is fixed, column 0 t and column 0 t prime are the same, and rho t and rho t prime are the same. And then when T2 is fixed, the expectation of this and this are the same, because in both the cases we consider all the x's uniformly spread over T1, everything that is not in T2. So the distribution is the same. Then we define bad to be those partitions we say are x bad if it satisfies this condition. So this is going against the statement of the lemma. Statement of the lemma was mu of the measure of the 0 partitions is at least something. So this the good, we say something is bad if the measure of 0 is less than the measure of the rho 1t, which is supposed to contribute to the measure of zeros, is strictly less than the measure of rho 0t, which is supposed to contribute to the ones. And white bad if it is similarly for columns. And we say t is bad if it's either x bad or y bad. Claim 1, the fraction of the probability that a chosen partition is x bad is equal to 1 is at most 1/5. So the most partitions are good. And the proof of claim 1 will be proved in the next lecture. Claim 2 relates the contribution of rho 0 t, column 0 t, just restricted from the good partitions. That itself is significant. Claim 3 relates the measure to the expectation of rho 0, rho 1, column 0, column 1. And finally, and putting it all together, we have the proof of the lemma. So most of this is algebra and very smart probability and calculation. It must have required a great deal of insight to see things this way and to put things together this way. So yeah, so it's very clever. And proof of claim 1, since we have already had a kind of a long recording, I will defer the proof of claim 1 to the next lecture. So proof of claim 1 is interesting, and we'll just see that alone in the next lecture. Okay, so we have had a kind of longish lecture going from page 1 to page 10. Yeah, this is page 10. All right, so I'll stop the lecture.